Hello everyone, and thanks for watching Edipedia World Videos. In this video, we'll learn about the working of a special kind of magnet called a bar magnet. Now, in this video, in the beginning I'm going to show you some similarities between electricity and magnetism, and these similarities we've seen in the previous videos again and again, and from that we'll try to create a hypothetical model of magnetism which mirrors how electricity works. And that model doesn't really exist in nature, but it helps us mathematically because we've already solved a lot of things with regards to electric fields and Coulomb's law. So why not create a hypothetical magnetism model that mathematically mirrors the model of electricity, because ultimately in the formulas there do seem to be a lot of similarities. So let's see what the basic similarities are. The magnetic field at an axial point due to a dipole. A magnetic dipole is a current carrying loop carrying a current I. If this particular side is towards the viewer, in that case the left side will be the direction of the magnetic dipole moment, which will be equal to IA. So if this is the direction of a dipole, then this particular line or any point on this line is called an axial position. Any point on this slide is called a broadside position. Right. Axial positions are also called ends-on position. So the B axial for a magnetic dipole moment we've calculated previously. It is equal to mu naught by 4 pi into 2 mu by dq, if this is the distance between the dipole and the point. Right. Also, the torque due to a magnetic field on a dipole is given by mu cross B, and of course mu is IA. What is the axial electric field? For a standard dipole, if this is the positive side, this is the negative side, then this is the direction of the dipole. If you take a distance d away, what is the electric field here? We've calculated it in electricity and in the video of dipoles, and it is equal to 1 by 4 pi epsilon naught 2p by d cube. If you go to the broadside on position, there is no factor of d. And the torque due to electric field on a dipole is given as P cross E, and of course the dipole moment is equal to QD. So we see a lot of similarities. D works like A, Q works like I, mu naught works like the reciprocal of epsilon naught, mu is the analog of P. So from these similarities, it does make sense for us to create a hypothetical model of magnetic forces which involves something which really does not exist in nature, which are the first part of the theory, and that is two magnetic charges. Let's say positive charge and a negative charge. Now, this doesn't exist in nature. Till date, we haven't been able to experimentally find positive and negative magnetic monopoles, are they're called. We have electric monopoles, for example, an electron or a proton, and we have electric dipoles, in which we take two monopoles of opposite charge and we put them near each other. For magnetic dipoles, there is no magnetic monopole. A magnetic dipole is simply a current carrying loop. But since there are so many mathematical similarities between electricity and magnetism, what we'll try to do is create a hypothetical model which mirrors electricity. The second assumption might be that the force due to the magnetic field on a particle that has a magnetic charge M will be MB. M is the symbol for magnetic charge. It is the analog of Q. MB is the analog of QE, F is equal to QE. Right? Another assumption we'll make is, and this assumption follows from these assumptions, the magnetic field produced by a single magnetic charge M is given by mu naught by 4 pi M by R squared R hat. Just like electricity is 1 by 4 pi epsilon naught Q by R squared R hat. Right? It can also be written obviously as mu naught by 4 pi M by R cube R vector, because R vector divided by mod R is R hat. If these things are assumed to be true, then the magnetic dipole moment can be written as MD, which will be the analog of QD. QD would be a small positive and negative electric charge placed a distance d apart. A magnetic dipole would be a small positive and negative magnetic charge kept a distance d apart. Again, the direction of the dipole moment goes from negative to positive, just like in the case of electric dipoles. So from now on, what we'll do is, all we need to do is, every time we have a magnetic dipole which has a dipole moment is equal to IA, we'll just try to replace it by MD, right? And we'll try to calculate an equivalent M and an equivalent D, and once we know that, we'll be able to use this M in these formulas, and we will get the right answer, even though this is really not what is happening in the universe, because like I said before, there are no magnetic positive and negative charges, right? But if it mathematically helps us, then why not? So what we'll generally do is, every current carrying dipole, so this is a current carrying loop. The current is going in such a way that if your eye is here, you'll see it going in the clockwise direction. So this side is towards the viewer, this side is away. That's why I haven't shown this. So this current carrying loop having a magnetic dipole moment mu is equal to IA, we can actually assume it to be a bar magnet having a positive and a negative charge. Now if this is the direction, then this is the direction of magnetic dipole moment, right? And if this is the direction of magnetic dipole moment, that means there will be a positive charge plus M here and a negative charge minus M here, and this distance will be D, and we will be able to write mu is equal to MD, right? So for this chapter, every time we see a current carrying loop, because like I said in the very first video of magnetic field, charges are what is fundamental to electricity, currents are what is fundamental to magnetism, and electric dipoles are the analog of magnetic dipoles, which are current carrying loops. So from now on, every time we see a current carrying loop, we replace it by a magnetic bar magnet, right, which has a magnetic strength of M and a distance between the two sides would be D. When we are talking about M in terms of the standard magnetic field, it is the magnetic charge, but when we talk about M in terms of the magnetic dipole, it is called the pole strength of the dipole, right? So M is the pole strength. It doesn't really exist, and if you are very careful to notice here, you'll see that M doesn't have a unique value, because we could take M to be twice its value and the magnitude of D to be half its value, and still everything would come out to be the same, right? So we have an inherent ambiguity in choosing M, but MD has to have a particular specific value. Now a standard solenoid does look something like a bar magnet, but it has one big difference with regards to an electric dipole. Within the solenoid, the direction of the magnetic field is opposite to what you would expect. So if this is a solenoid and it carries current in this direction, then now I'm not drawing individual loops, I'm just drawing this, and in this case, when we talk about a solenoid like this, we don't talk about the current in a solenoid or the number of loops per unit length. What we talk about is the current per unit length. So for example, if we take a small distance, a small thickness, there will be some current flowing through it. If we double the distance, twice the amount of current will be flowing through it. So we define current per unit length for a solenoid. Anyway, the magnetic field lines in a solenoid look something like this, right? And you can work it out on your own. If you take magnetic dipoles and calculate their magnetic field at different points, this is the pattern that will come out to be, and this is the pattern which we've seen when we put bar magnets on a paper of electric filings. Maybe some of you have done that experiment in some lower classes. This is the sort of pattern that is made. Right, and in this case, the direction of the magnetic dipole is in this direction, because if you're looking at it from this direction, the current will seem to be clockwise, right? So this is the direction. Now, what are the electric field lines of an electric dipole? If you have a negative charge and you have a positive charge, then the direction of the electric dipole is also this, and these are the direction of electric field lines. Now here we see one major difference between the electric field lines and the magnetic field lines. Outside they pretty much follow the same pattern, like this, going here and going here. But within the material of the bar magnet or the solenoid, the magnetic field goes from left to right, whereas the electric field goes from right to left. And that is actually evidence of the fact that magnetic monopoles do not exist, because electric field lines can actually start and end at a point. If electric field lines start at a point, that point is a charge, a positive charge. If electric field lines end at a point, that point is a negative charge. But magnetic field lines never end, because we do not have any magnetic positive or negative charges. So that's why if you leave a particle here, it will go somewhere else. It will not necessarily go in this direction, because it will have some velocity and some acceleration, and the motion will be complicated. But the direction of magnetic fields will always be like this, and you can see these loops do not start or end anywhere. They just go on forever and ever. Right? So this is the biggest difference between electricity and magnetism, that electricity has electric monopoles which are positive and negative charges, whereas in magnetic field you do not have any monopoles, and the only thing that produce magnetic fields are moving charges, which are also called currents. Another thing we see is that we assume a solenoid or a bar magnet to be infinitely long, and in that case all these lines would be completely straight. But if it is not infinitely long, even then within the central region these will be completely straight, because we can assume it to be very long if we are looking at just at the center. When you start reaching at the ends, they will not be completely straight, and they will have what is called end effects, which means they won't behave completely like an ideal magnetic dipole. So what generally happens is, due to these end effects, if this is the length of the magnet, which is called the geometrical length, then the magnetic monopoles are generally not present in the ends. We don't assume them to be present in the ends, because that doesn't give the right answer. That should be the proper statement. They're actually present a little bit inside, minus m plus m, and that is because of the end effects when we assume that it is infinitely long. Right? Whenever we talk about solenoid, we'll assume that it's infinitely long, or we are near the middle of it, so that the end effects do not matter much. But this distance between these two is called the magnetic length. And experimentally it has been found for solenoids that the magnetic length by the geometrical length is equal to 0.84. This is a constant. Right. So the magnetic poles should be assumed to be present slightly inside the material to negate for end effects. Right. Now, another convention generally is that this magnetic length is not taken to be small l. Just to make the mathematics easier, it is taken to be 2l. Right. So the magnetic length is 2l, and the magnetic pole strength is m, because we have minus m and plus m. And so now we talk about capital M, which is the magnetic moment or dipole moment, sometimes dipole is omitted, of the bar magnet, and we get the equation m is equal to 2ml. Again, this is pretty much like P is equal to QD, except we've taken the distance between the positive and negative side to be 2D instead of D. Right, so it is ml, except we've taken the distance between them to be 2l. That will become clear when we start solving for magnetic fields due to this bar, and we'll see that if we had taken it to be l, we'll keep seeing l by 2 everywhere, and we don't want to see l by 2 everywhere. So by convention you should remember this. The magnetic length is denoted as 2l. So if you are given the magnetic length in a question, and you think of a formula which you remember, in applying that, and in the formula you have something like d square minus l square, remember that l is not the magnetic length, it is half of the magnetic length. The magnetic length is taken to be 2l. Now this negative end is usually called the south pole of the magnet, and the positive end is usually called the north pole of the magnet. And we'll see terrestrial magnetism or the magnetism due to the earth in a later lecture. But right now I can tell you that the magnetic field of the earth is something like this. It goes like this, the field lines, if this is the axis of the earth, right, south to north. And these magnetic field lines, they very much resemble the magnetic field due to a bar magnet placed at the earth's center. And that is why often you'll hear this phrase that the earth's magnetic field can be replicated by a bar magnet placed at the earth's center, because experimentally that's what we found out. Now let's look at what happens when we keep a bar magnet in a constant magnetic field. So let's say we have a magnetic field pointing upwards, and we've kept a bar magnet at an angle, right? Somewhere here might be minus m, somewhere here might be plus m. That doesn't matter. Right now only the direction matters. This is the direction of m. And we know the value of m. It is 2 ml, but we won't use that because all we need is m. This is the magnetic field B. Let's say the angle between them is theta. What is the torque on this bar magnet? It is equal to m cross B. Right? Now let's say we left this bar magnet initially in the horizontal direction, and now it's at theta. Initially it was at 90, now it's at theta, and it moves another d theta. Right, the torque is trying to take it in this direction, so it will move another distance d theta. And actually what should be better was if we take this to be theta, then d theta would be a positive change in theta. Right, so now what is the work done by the magnetic field? That will be m into b into sine of the angle between m and b, which is 90 minus theta now. So mb cos theta. Right, this is the torque. This into d theta. This is the work done by this magnetic field. Right, so what is the magnetic potential energy? We'll try to define it just like the electric potential energy, and that is the negative of the work done by the magnetic field. Right, so the negative of the work done by the magnetic field will be the change in potential energy. We integrate it and the angle goes from 0 degrees to theta. So what we get is u theta minus u0 is equal to the integral of cos theta will be sine theta. So we'll get sine theta minus sine of 0. That is sine theta, but there will be minus sign. So minus mb sine theta. If we take u at 0, that is in this direction, to be 0, remember we always have the freedom to choose 0 at any particular point in potential energy. Then we get the equation u theta is equal to minus mb sine theta. Now let's call this angle alpha, which is 90 minus theta. So it can be written as minus mb cos alpha. And since alpha is the angle between m and b, it can be written as minus m dot b. Right, so we see another similarity between this and electric field. The potential energy in an electric field would be minus P dot E for an electric dipole, and for a magnetic dipole in a constant magnetic field, the potential energy is minus M dot B. But remember, this is assumed when we take the potential energy to be 0 when the magnetic magnetic moment and the magnetic field are perpendicular to each other. Right, so this is the potential energy. Now let's look at the actual field created by a magnetic bar. Actually this video I think is long enough. We'll calculate the magnetic field on the ends on in the broad zone position just like we did for electric dipoles due to a bar magnet, but we'll do that in the next video.